Hello, now we're going to talk about Newton's law of gravitation. Now, to frame this correctly, we have to go back into Newton's laws. Newton's third law, precisely. You may have heard it like this. This is the way that you'd be asked to write it in the exam. If object A exerts a force on object B, then object B exerts an equal and opposite force of the same type on object A. Now, that's not what Newton said. Newton said for every action there is an equal and opposite reaction, but that won't get you the marks in the exam. You need to talk about objects A and B. It means that between the Earth and the Moon there is a force of gravity, and that it is equal and opposite. But you may say to yourself, how can it be equal and opposite? If the Moon is much smaller than the Earth, how is it capable of pulling on the Earth with the same force as the Earth pulls the Moon? Well, the key thing is this: the force between them is equal and opposite, but the effect that force has is in inverse proportion to the mass of the object, which means the Moon's force on the Earth doesn't have very much effect because the Earth is so big, whereas the force acting on the Moon from the Earth has more of an effect because the Moon is so small. And just while we're on this subject, let's just clear up this little error of thinking. The very best example of Newton's second law is not a book placed on a table. Though initially it looks like a perfect Newton pair with the weight of the book acting down and the supportive reaction force of the table pushing up, this does not count. You shouldn't use it as an example because, quoting Newton's third law of motion, the force pairs have to be of the same type, and these are not. One is due to gravity and one is due to the elastic sponginess of the solid material of the table, not the same type of force. So what's really going on here? Well, there are actually two pairs of forces. There's the force of gravity on the book by the Earth, and there's the force of gravity on the Earth by the book. These are equal and opposite. Now, you have the force of compression on the table, and that is equal and opposite to the force of reaction supporting the book against that compression. Now, because two of those forces are completely invisible to us as we look at a book on the table, it looks like there is only the weight of the book and the reaction force of the table. But we actually know that it's two pairs. And so this is not the example you should cite when talking about Newton's third law of motion. So let's go back to 1666. Isaac Newton was sent home from Cambridge due to the bubonic plague, a pandemic that resulted in him travelling back to Woolsthorpe Manor, where he had time to think about the deeper things of life, including physics. Now, much later in life, when Isaac Newton was a famous man, he was being spoken to by a person called William Stukeley. And William Stukeley was writing Isaac Newton's memoirs, and he asked Newton, "How did you think of gravity?" And Newton reflected back to that heady summer of 1666, and he said that he was stood in the garden at Woolsthorpe Manor, observing the apple trees. He said, "Why should that apple always descend perpendicular to the ground?" thought he to himself. "Why should it not go sideways or upwards, but constantly to the centre of the earth?" Now, that apple tree is still there in the garden of Woolsthorpe Manor, perhaps one of the most famous trees in the world. And there is a photograph of me stood with kind permission inside that perimeter fence, taking an apple from the Isaac Newton's tree. Now, it's very possible that Isaac Newton, being a biblical scholar, fully understood the significance of what the apple represented in the biblical story, the apple of knowledge, plucked from the tree of knowledge by Eve and given to mankind. So there could have been a little bit of imagery play going on here, but certainly he had apple trees, and it's sensible enough that apples falling would have given him an understanding of gravity acting downwards, the same force that provided the centripetal force that kept the moon in orbit around the Earth. And this is how we believe he started formulating his universal law of gravitation. So when did he write it down, and how did he write it down? Well, he was piecing together the work that would eventually become the Principia Mathematica. And to start with, he actually recorded it in some smaller books that he then amalgamated into 3 volumes. And so it's in the 3rd volume, the 3rd book in the Principia, that he writes this, and it's about Jupiter's moons. He says that the forces by which the circumjovial planets, that's the moons of Jupiter, are continually drawn off their rectilinear motions, that's drawn away from their straight lines, and retained in their proper orbits, tend to Jupiter's centre, and are reciprocally as the squares of the distance of the places of whose planets from that centre. So there we have it, by the square of the distances. So this was the inverse square law. And Isaac Newton records that when he first wrote this down, it was 1685, because at the same time, outside his room at Trinity College, there was a procession of people proclaiming that James Stuart was the new King of England, which means the date that gravity was first written down was the 6th of February 1685. And yet there had been some trouble, as we shall now see. But first, what exactly was Newton suggesting? Well, he was first of all suggesting that the force of gravity between 2 objects was in proportion to the product of both of their masses. Now, if you read the Principia, Newton's dealing with the products of various quantities starts right at the very beginning in the very first definition, where he says that the mass is the product of the density and the volume, that it's these 2 things multiplied together that give you the mass. And it says that multiplying any one of these by 2 doubles the actual mass itself. Here, if I doubled either of the masses, it would actually double the force between them. But if I doubled both of the masses, it would quadruple the force between them. That's how these relationships work. He also pointed out that the force was inversely proportional to the distance of the object squared. It's what we would call an inverse square law. If you imagine the field lines spreading out and separating radially over ever greater and greater areas, then it's quite obvious to us that it would be a 1 over r squared. But it wasn't obvious at the time. For in the late 1670s, the then president of the Royal Society was meeting with the other members of the Royal Society at their usual coffee house after one of their meetings, and whilst Newton was not present there, the conversation got on to Isaac Newton, and flashing his mouth off, Robert Hooke, who's obviously famous for using the microscope and Hooke's law of stretching of springs, started saying that he had given the invention to Newton. He actually claimed that he had, in person, explained the ideas to Newton, that Newton was now representing these ideas as his own. Now, no such conversation had happened, in fact, as we have got documented proof that Robert Hooke was not being truthful when he said that he had directly given the invention to Newton. Of course, everybody else there knew Newton and had spoken to Newton for the last decade about the inverse square law. They all knew that it was his invention. Sir Christopher Wren, who designed St. Paul's Cathedral, as well as much of London after it burned down after the Great Fire of London, didn't believe Robert Hooke and actually challenged him at the coffee house and said, we were all of the opinion that you, as in Isaac Newton, should be the inventor. So they shot down Robert Hooke. But Robert Hooke was not going to stop there, because having gained no influence of the esteemed colleagues of Isaac Newton, Robert Hooke went to Newton himself and tried to insist to Newton that Newton had stolen his ideas, even though there had been no communication at that point about this between the 2 men. So, having harangued Isaac Newton didn't take very kindly to this, and this is what Isaac Newton said about Robert Hooke. Should a man who thinks himself knowing and loves to show it in correcting and instructing others come to you when you are busy, and notwithstanding your excuse, press discourse upon you, and through his own mistakes correct you and multiply discourses, and then make his use of it, to boast that he taught you all he spake, and oblige you to acknowledge it, and cry out injury and injustice? If you do not, I believe you would think him a man of strange unsociable temper. So yeah, he really annoyed Isaac Newton in this moment. He'd basically caught him at a moment where Isaac Newton was not expecting to have a discourse about gravity, told him some incorrect things, and then later claimed that that conversation was the time that he had told Isaac Newton everything he knew, which of course was a complete fabrication. Newton, then looking into what Hooke had actually said about gravity, realised that he had read it before. You see, Newton was an avid reader. He read all night long, and he had got many, many books. His library was vast. He also had a very good memory for things that he had read. And what Hooke was explaining was the following, that the planets are being pulled towards the sun by a force, and that the force diminishes with distance. And these 2 points together sparked a little bit of memory of Newton, and Newton, in pure excellence, remembered exactly who had originally written this. It was a person called Borelli. And so what he had realized was the ideas that Hooke was passing off as the ideas that he had apparently taught Newton were not only things that he had not taught Newton, he had taken them directly from another scientist without actually explaining that this was Borelli's hypothesis. Naughty, naughty. So Robert Hooke had not managed to convince anyone at the Royal Society that he was the person that invented the inverse square law. He was also not able to get any traction with Isaac Newton himself, who just rejected the idea because Isaac Newton knew how he formulated it because he was there when he did it. But he wasn't going to let it go. He hung on to it for a very long time. I mean, 1689, which is quite long after the event, he didn't want future generations to get a distorted view of his influence here. So he wrote to Anthony Wood, the Oxford chronicler, like a historian that wrote about the present times and would write things down. He wanted to leave something for the future that suggested that the consensus at the time was that he had discovered the inverse square law. So he asked Anthony Wood to distort history, or the recording of history, so that future people would believe that he had discovered it. And the words that he had Anthony Wood put into the Oxford Chronicle about himself is this. Get ready for this. It's a belter. That his, Robert Hooke's, discovery of the inverse square law is the greatest discovery in nature that ever was since the world's creation. It never was so much as hinted at by any other man. Wow, that's really desperate, isn't it? So why should it be an inverse square law? Well, I can think about it in terms of the field lines. If the field lines are spreading out radially from any particular place, then they're going to spread out. For every r, for every like r and 2r, then they're going to spread out over ever larger areas. So at 1r, the area over which they spread is r squared. At 2r, it'll be 2r squared, which is 4 times the area of r squared. And at 3r, it's 3r squared, which is 9 times the area. And given it that it is spread out over ever larger areas, then the amount passing through any one of those is 1 divided by the area squared. It's being diluted. Now we find that this is true in all sorts of situations where things are radial, including the intensity of light as it spreads out from a radial source. It decreases with 1 over r squared in its intensity. So here it is, the force between any 2 objects that have mass. Now, what's in here? First of all, capital M is normally the larger of the 2 masses if they are of unequal masses. And that's what we do tend to see, the Earth and the Moon, or the Sun and the Earth. One is big and one is small. And so the one that is creating the larger, stronger gravitational field is the one that we would call large M. Now, the force is proportional to the product of these 2 masses, and inversely proportional to the distance between them squared, r squared. But you can see at the front there's 2 more interesting things. First of all, a negative. The force is always acting back towards the centre, in the opposite direction to which r is getting bigger. That makes sense. If r is measured from the middle and gets bigger as you go further away, then the force is always going to be pointing backwards as a vector towards the centre. And so that's why we must always say negative. And the second thing is giant G, or big G, just there, the gravitational constant. Now this is an arbitrary constant equal to 6.67 times 10 to the minus 11 Newton meters squared kilograms to the minus 2. This is an expression of how weak gravity is. Now this was the thing that was determined by Cavendish with the lead balls experiment. But what does it really mean and why is it there? Well, why is it there is quite easy. When they assigned the units to mass as kilograms and the distance as meters and force as newtons, all of these were picked rather arbitrarily. They weren't supposed to be a part of the same unit system. They were just, well, a meter is about the length of my arm, and a kilogram is about the length of a lump of metal, and a newton is about the weight of an apple. So these aren't naturally going to be compatible with each other. We have to put a constant so that these could be numerically equal. But what does the constant fundamentally mean? Well, if I had two 1 kilogram masses at 1 meter apart, then what I would have to do is multiply that by 6.67 times 10 to the 11 to work out the force that it would produce. So in a sense, two 1 kilogram masses 1 meter apart would produce a force of 6.67 times 10 to the minus 11 newtons. That's tiny. That is such a tiny little force between them. The only reason why gravity is the dominant force is that the planets producing these gravities are just so massive in the first place. How does this force relate to a graph? Well, I could plot it. Slightly strange graph I've drawn there, but just don't look at the details too hard. It's 1 over r squared. So what we can see is that it is greatest at the surface of the planet. It goes 1 over r inside the planet, and it's 1 over r squared outside of the planet, rapidly decreasing. If I plotted a graph of force against 1 over r squared, I get a straight line whose gradient is equal to minus gmm, if you ever see that. So here's an interesting question for you. So we've got the Earth, the Moon, and the space station, but they're not all in a line. One of them is at right angles. The space station is at right angles to the Earth-Moon line. And given the distances and the masses, what would be the force of gravity acting on the space station when the Earth and the Moon were in those different places? See if you can have a go at solving this. Right, let's work the problem. So first of all, we need to find the distance of the space station from the Earth's center. And that's going to be quite easy to do. Because if RE is equal to 6371 kilometers, we're just going to add it to 400. And that gives us 6771 kilometers. And then we're going to now convert this into meters because everything's going to have to be meters in the end. Just like that. Now, the distance from Earth to the Moon is just up here. We're going to convert that into meters as well. 3844 times 10 to the 8 meters. Now, since the space station is at right angles to the Earth, then the distance to the Moon, so distance between space station to the Moon, to the Moon center, is as follows. It's going to be basically, there's the Earth, there's the Moon, there's the distance rm, and there's the space station over here. So rm is going to equal the square root of the distance between the Earth and the Moon squared plus the distance from the Earth squared. So when we substitute these in, we get it as 3.845 times 10 to the 8 meters. Just compare, let's see how similar it is to this number. They're very, very similar because there's not a lot different. Now, it makes sense for us to calculate the force per unit mass. So what we're going to do is, rather than calculate that F equals minus gm over r squared, we don't know the mass of the space station. So instead, what we're going to do is we're going to work out the force per unit mass, which is g. The force per unit mass is that, which will be equal to minus gm. The other m cancels out r squared, but we can do that for all of the objects. So The force from the Earth, therefore, on the space station is going to be 6.674 times 10 to the minus 11, that's G, times 5.972 times 10 to the 24, that's the mass of the Earth, divided by the distance it is above the Earth's centre, which is 6.77 times 10 to the 6 squared, and so that equals 8.69 newtons per kilogram, slightly less than the 9.81 that we see here on the surface of the Earth. So the force from the Moon is going to be 6.67 times 10 to the minus 11, as before, times 7.34 times 10 to the 22, which is the mass of the Moon, divided by the distance to the Moon squared, 3.845 times 10 to the 8 squared, which is 3.31 times 10 to the minus 5 newtons per kilogram. That is tiny. So what we know is that this represents basically depending on how we're writing it, we'll call this the y component towards the x component is towards the Moon, so we'll call this x. The y component slightly downwards. So the net force is going to be, we'll call this x, and we'll call this y. That makes more sense compared to this diagram here, because this is x over here, and this is y over here. No, that really doesn't make sense. I've done it the other way around. I'll just rub those out. Because what we're talking about is this really, this is y. Okay, so f of x is about 3.31 times 10 to the minus 5 newtons per kilogram. We'll say f of y is equal to, it's going to be equal to f of the Moon in the y direction minus the force of the Earth, so minus 8.69 times minus 8.69 newtons per kilogram, which means that the net force is just equal to the square root of those two, f of x squared plus f of y squared. It comes about 8.69, so it's almost exactly the same as the force that it feels from the Earth. That the Moon's contribution is absolutely tiny. And if we work out, well, what is the angle difference between pointing directly at the Earth, then we just need to use a little bit of trig and do f of x over f of y. And it's about 2 times 10 to the minus 4 radians, which is equal to about 0.011 degrees. So really, the space station feels nothing from the Moon. It feels everything from the Earth itself.